X-ray diffraction is a powerful tool that allows us to find the structure of different crystals. X-ray diffraction works basically the same way as an optical grating. In the diffraction grating, we had periodic openings or periodic slits, which created constructive interference for certain conditions. These conditions would be that the path length of the different sources of light, beams of light, would be some integer value times the wavelength. This would keep them in phase. We call this the Bragg condition. As long as two light waves have some path difference, which is an integer times a wavelength, they remain in phase. The peaks remain with the peaks, the valleys remain with the valleys. For a crystal plane, the Bragg condition occurs when twice the distance between the planes times sine theta is equal to an integer times the wavelength. Here we can see how this happens. In this ray, we have the light reflecting off of the top surface of the crystal. One layer down, a ray will travel a distance equal to this red arrow plus a distance equal to this red arrow, which is d sine theta. So 2d sine theta is going to be equal to m lambda for the condition of constructive interference. X-ray powder diffraction takes samples ground up to a fine powder, as the name implies, and wherever we have Bragg's condition met, we will get a strong constructive interference. We'll get a strong peak. The X-ray source basically comes from accelerating electrons and hitting a metal target, and then we use a type of filter to basically keep the X-rays monochromatic or one wavelength. Essentially, we use another crystal to select only one wavelength. The X-rays then impinge on the sample, and the sample is rotated some angle theta, while the detector is rotated some angle 2 theta. Whenever the condition is met, the Bragg condition, we will get a peak. One of the simplest crystals is the simple cubic structure. In this, we have a basic cubic structure. Sodium chloride, for instance, is a simple cubic. And the major planes that we have are the 1, 0, 0 plane. These are just basically the planes of the cube. The 1, 1, 0 plane, which is a diagonal in one direction across the cube. And then finally, this diagonal plane right here. And if we place the sample in an X-ray powder diffraction spectrometer, we can see each of these different planes will reflect strongly at the Bragg condition, at a particular wave, at a particular angle. The 1, 0, 0 plane has the greatest distance between the crystal planes, and therefore its peak is at the smallest angle. The 1, 1, 0 is slightly closer, therefore its peak is at a slightly greater angle. And then the 1, 1, 1 plane has the smallest distance, and therefore its Bragg condition is met at the largest angle. Here's another version of X-ray powder diffraction. Instead of using a rotating detector, this simply uses either film or a detector array. Now the beam of X-rays is sent toward the sample and it is diffracted at each angle representing constructive interference, the Bragg condition for each crystal plane. Here you can see several crystal planes represented by these rings. Single crystal X-ray diffraction, as the name implies, doesn't break the sample down into a powder, but rather keeps the crystal oriented in one direction. Again, an X-ray source is used, which is monochromatic, meaning it's basically one wavelength coming in. And this creates a more complex pattern, which is then recorded by film or a detector. X-ray diffraction was very important in discovering the structure of DNA. The work was conducted by Rosalind Franklin and a graduate student, Raymond Gosling, and then further analyzed by Watson and Crick, who received the Nobel Prize for their discovery. Now, there's a bit of controversy about who discovered the double helix in DNA and who should have received credit. Watson and Crick received the Nobel Prize for discovering the structure of DNA. In some respects, Franklin was not eligible to receive the Nobel Prize because, unfortunately, she had passed due to ovarian cancer. However, Franklin was not credited during her lifetime for her contributions, so it's probably unlikely that she would have received the recognition of getting the prize with Watson and Crick. Of course, during the 1960s, when the discovery was made, there is still quite a bit of sexism in physics. So again, many argue that Franklin's diffraction work really was not given the credit that it should have been, even today. The Curiosity rover is another example of where X-ray diffraction is used. Now, this roving laboratory has to be very compact and be able to analyze its samples with a great deal of sophistication. One of the instruments that it uses is called I hope I'm getting this correct, the K-min, which helps identify mineral types using X-ray powder diffraction. Basically, what it does is it uses a beam of X-rays to perform X-ray powder diffraction and then determine the crystal spacing in the minerals from each of these samples. Now, here's an actual picture of the device. I believe what this is right here is this is a screen that helps filter the dust so no rocks get into the sample collector. And then inside this machine, the X-rays will then hit the target. And over here, we can see the detector array, which produces the ring pattern from the different diffraction angles. The smaller diffraction angles are closer to the center. The larger diffraction angles are further from the center. Now, I don't have a lot of experience with X-ray crystal diffraction. However, according to the image that I got from NASA, I should have credited it, the minerals that were observed in this particular sample included feldspar, pyroxenes, and olivine. These are very typical minerals that we expect in igneous rocks.